So my background is in, my original undergraduate degree was in applied math, engineering, and physics. So I primarily think of myself as a physicist with an applied math background as well. And I learned a little bit of nuclear engineering along the way, so I have some engineering background that goes along with that. And after doing that at the University of Wisconsin-Madison, I went to MIT, where I studied meteorology and worked on a paleoclimate problem associated with the elevation of ancient mountains, and trying to infer that from a statistical standpoint based on plant leaf morphology. And finally, broadly now, I've switched after my graduate degree. I started working on modern day climate issues and sort of addressing the uncertainty in climate projections at the large scale. Global mean temperatures primarily, but also trying to understand the differences between the tropical response and the high latitude response as a result. And now when I moved to Penn State, I stayed at MIT for about 18 years, and I now am at Penn State. And the new thing that I started there is getting into additional things related to climate risk and how do we assess the uncertainty and then propagate that into the impacts community. And from a physics perspective, I'm very interested in the issue of how do different climate models produce different regional responses, and how do we go about characterizing that from the atmospheric model perspective. And so I've been working a lot on teleconnection patterns and how do we assess the teleconnection information between the tropics and the rest of the world, and then try and characterize the uncertainty in the model structures as a result of that. So I thought I was going to take about 10 minutes and have everybody give me their ideas as to what they think are important things that they want to learn from the session. So I'll take 3 answers from the audience in terms of what's the one thing that you really want to learn while you're here. One? No. 2. You're going to have to start talking sometimes. 1.
Quantifying uncertainty.
What? Any specific types of uncertainties? All of them. Excellent. OK. More? Yes?
What kind of uncertainties are associated with the impact sectors? I mean, I'm coming from the hydrology department, and they are very interested in knowing how much is the uncertainty of climate model outcomes.
So the answer for the camera here, I'll repeat it a little bit, is you want to learn about uncertainties as they relate to impacts research. You're a hydrologist, and you're interested in how the climate models are producing information that feed into the hydrology and hydrologic forecasts for impacts.
The sources of uncertainty, I mean, the GCMs, whether they have the most important uncertainties, or the input parameters, or initial condition, or parameters.
Excellent. OK. One more?
Confidence in model predictions.
Confidence in model predictions. Do we have them? That's a good question. OK. The other question I have is I'll say, how many of you are atmospheric scientists? Raise your hand. OK. How many of you are statisticians? That was about half the room. A few statisticians, slightly few more, less. How many of you would say you're hydrologists? Geophysicists by training? Any oceanographers? Yes. Any land surface specialists, carbon cycle specialists? Not so many. OK. Any people working on impacts specifically? Climate change impacts? Are there any managers in the room that are managing policy decisions for their companies or for their countries or for their communities? OK. So you start to get a sense as to what I'm starting to get a sense. I hope the other lecturers are starting to get a sense as to what the group is here and what the interests are. And you'll each have a chance to talk about this in your own introductions later on. But I look forward to hearing from you. from my perspective, I want to learn from you guys what are the interesting things that we need to provide to you in the uncertainty realm. And I think that's what, when I get into these big workshops like this is one of the first things that I want to learn from you. You guys are a cohort of people that are going to go out and work together, I hope, over the next many years, together on issues of uncertainty in climate change research, either from the purely statistical side or from the Earth system modeling side. And I think that's what we're trying to get from, we're trying to add to your repertoire of tools that you can use to apply to these particular problems. Okay, I wanted to thank the organizers and ICTP for funding this and getting everybody together. This is wonderful. I think it's going to be a fun week. All right, so getting into the actual details. All right, sources of uncertainty in climate predictions. There is a big distinction these days between predictions of climate as opposed to projections of climate. And most of what I'm going to talk about today is trying to provide language that we can all use to talk about uncertainty. And maybe everybody's already up to speed on these sorts of things. Sometimes we need to have a common set of things that how we discuss problems. And so the next thing is introduction to climate model hierarchy, climate system response as a whole, and characterizing model uncertainty in terms of rather than necessarily quantifying model uncertainty. I think often we know things that we can quantify, and we go after those particular issues directly. But more often than not, we're not necessarily, we may not get all of the various components that need to be assessed, and so we're left with qualitatively characterizing the uncertainty, placing ranges or bounds on things that we know, or identifying very specific systems, which then have to be further investigated through sensitivity analyses in order to understand how they behave. Or there are things that the models just cannot do. They don't have the actual mechanisms. I use that word for Charles, and or processes, as I call them, in the models that are actually then we can then assess. And if those processes are missing, then your model is fundamentally then missing a maybe perhaps an important part of the uncertainty overall. Okay, so what drives uncertainty in the climate system response? And this is in the program. Ben Booth and I were working on a lot of these ideas, and we shared notes, and so it says inputs from Ben, and you'll see these courtesy of Ben Booth at the bottom when I've borrowed something from something that he's done. So over here we have sort of characterizing the uncertainty in the future climate change response of the system. It's being driven by uncertainty in two very specific areas. It's hard to separate the world any further into two larger categories than these, I would say. The first one is the humans, the socioeconomic processes, and how they're proceeding over the next 100 years. And are people familiar with the IPCC fairly well? Raise your hand if you are, or raise your hand if you want to hear a lot more about it. Hear about, first of all, the IPCC process. If you're familiar with the IPCC process. If you're not, raise your hand. Okay, so I can sort of go into this in detail, but I think as a workshop, ask as many questions as you can, because we're here for you. Don't hesitate to interrupt me. I will stop at any point in time to answer questions as best as I can. And if I only get through 5 slides, at some level I know that I'm responding to your needs rather than blasting you with information that I think is important. So, okay, so socioeconomic policies are here. Earth system processes are here on the right. And at some level, the socioeconomic processes are forcing the system. The changes in carbon dioxide emissions are driving concentrations in the future. And so that's part of the driving factors. Also, the way we use land And I'll add up my points right here. So we have these various factors are driving the uncertainty in future forcings to some degree, with a coupling over here on the right to Earth system processes as well. We know that energy consumption, land use change, agriculture are going to be contributing to the carbon cycle, and therefore the carbon cycle is part of the Earth system response, and that's then going to be the Earth system processes are also going to be contributing to the being driven by the socioeconomic processes as well. Okay, so population growth, economic growth, future technologies, energy consumption, and land use change and agriculture are characteristics that are driving the uncertainty in the humans' forcing of climate on long time scales. On the Earth system side, we have key processes influencing climate change include the feedbacks in the climate system. Are people familiar with the concept of feedbacks as a whole? Okay. We add a little bit. It's changing temperature, for example. That changes the climate system. The climate system then further adds an additional warming by its internal response or the internal feedback as a result. That's a very engineering-oriented concept, and it not necessarily gets into I would say, the general physics community or math community as a result, and so I think that's important to understand. We've identified some of the major feedbacks here which are contributing to the uncertainty and future changes. Clouds is the main one. Clouds are obviously, we look outside today, we have a nice cloudy sky. But if we have the distribution of clouds in the atmosphere, the low-level clouds are going to be radiating at a certain temperature that's close to the surface temperature. But they're also going to be reflecting sunlight back to space. And so there's a combination of both a short-wave feedback as well as a long-wave feedback in terms of their overall uncertainty. Sea ice is affecting the high latitudes. Carbon cycle is then assessing once we put a certain amount of CO2 in the atmosphere, how much of that CO2 is going to stay in the atmosphere, how much of that CO2 is going to be going into the ocean. And as the Earth warms, there's going to be a stronger ability for the land to absorb more CO2, but also the oceans are going to be absorbing less CO2. So you have a balance of the feedbacks in the carbon cycle being addressed here as well. The ocean's delay. The ocean is acting like a large heat sink and delaying the eventual warming. The strength of the forcings are determined by the microphysics as well as the radiative transfer properties within the system. And then we have this last one here is the variability in the system. And the variability in the system is something that I want to think about quite a bit and hopefully provide you with some basic ideas. Any questions at this point? This is all very high level, and I just wanted we're going to get into details either today with what time I have left or on Wednesday in a little bit more detail. Yes. What's your name?
My name is Jose.
Jose. Okay, Jose.
Well, before going to the uncertainty quantification, I have a question.
Mm-hmm.
Regardless of socioeconomic processes that will produce an additional source of uncertainty, I'm not sure whether the output of seasonal forecasts are reliable or not. So I'm mentioning about the seasonal forecast because there is no socioeconomic processes for seasonal forecasts for the carbon dioxide and things. So the output of seasonal forecasts are not quite reliable, I think, at the moment.
So I think that's an area that we're going to get into in a lot more detail, I hope. Several people are going to be talking about regional climate modeling. And the regional climate modeling of the future has to be verified by looking at the present day conditions or the ability to make forecasts on seasonal to a few years forecasts. So that short range climate forecast, we would call it. And I think that's an important area that where we're trying to identify when are we making predictions that can actually be tested by the models, and how do we go about there's a lot of terms which have been used over the years in terms of evaluation of the models, validating the models, falsifying the models? How does that process of scientific inquiry lead to a better understanding of the system and thereby help us reduce the uncertainties as the projections go out to even longer timescales? I didn't ask how many people are interested in, say, the next decade more than they're interested in what's happening at the end of the century. Yeah. So I think there's a lot of people that are trying to assess risks, and the seasonal forecasts are the type of information that are going to be necessary for those types of issues. So I think we're going to get into that quite a bit, I hope. More? OK. So what I wanted to do is introduce some examples of these things as they come out of the IPCC process. And how do we go about identifying these various sources of uncertainty in the system? So my first example is looking at a slide from Chapter 12, the long-term projections chapter of the IPCC in the 5th assessment report. We have a lot of information on this diagram, and there's a lot of uncertainty information in this diagram. And I'll bet a lot of it doesn't translate into the uncertainty quantification that we're really talking about here in this meeting. And I think that one of the issues of the presentation of uncertainty information like this is what we're trying to improve as we move forward with the climate science within the climate science domain. On this diagram, we have the socioeconomic factors here shown by the different colors. These are scenarios that are moving forward in time. Everybody, I think, is familiar with this. A low scenario in red, a high scenario in red, a low scenario in blue, and then the historical period from 1850 to 2005, I think, in these models is shown here as well. But the key factor here is that we have a range of models that are presenting a certain level of uncertainty in their prediction of what their response to these very specific scenarios in the future. And in this particular figure, we have models which end in 2100 and are then not included as they go forward to the year 2300. So it looks like there's a range of uncertainty here for the RCP 8.5, which is clearly larger than the uncertainty 1 year later in 2101. And that's only because we have a lower number of models that are assessing the range of uncertainty in that particular forcing. So this is the type of thing is we're assessing uncertainty with an ad hoc collection of models, which we call a multi-model ensemble. And that then is being used to assess what the range is as we go forward in time. The other is we have the 3 different scenarios. And so we have the number of models which were used to assess the uncertainty in each of these scenarios differs depending on the scenarios. So we have 12 models for the red one in this region after 2100, 17 models for RCP 4.5, which is equivalent to a CO2 doubling. And the 12 models then were used again for RCP 2.6, which is then, so we have this mismatch of our assessment of the uncertainty depending on which model we're actually going to be which scenario we're trying to assess. We go into the period between 2005 and 2100. Now we have 4 different scenarios. We have between 25 models in the orange case for RCP 6.0 up to 39 models for RCP 8.5. And that then is an issue of a combination of initial condition uncertainty, internal variability in the system, and as well as the uncertainty in the actual response of the overall response of the system. And I think for Ben's sake, I'd say that in this particular scenario, these are not necessarily Earth system models that have the carbon cycle feedback included in them. And so each of the models which has used the RCP has not yet included the uncertainty in the carbon cycle response in their results either. And that would then further increase the uncertainty And so keeping track of these issues when we look at IPCC information is a major headache, or a key task that people like us are really interested in terms of making sure we understand that. Okay, so we have this combination of forcings and model response. That was in Chapter 12, and now we look at what was presented in the Summary for Policymakers. Same sets of runs, but now they've eliminated the RCP 6.0 and the RCP 4.5 from their figures. They again show the number of model runs that were used in each particular case, but now we have another presentation of uncertainty, and it can be, unless you actually go into the chapters within the IPCC, you wouldn't necessarily see the differences across these particular cases. And then on the bottom here, we have Northern Hemisphere sea ice extent. Again, a different set of models, a different set of scenarios, and we see that the smoothness that we see out to 2100 in the future response of global mean temperature is actually much more jagged here in terms of what's going on in terms of the bounds as we move forward in time. And this now is a measure of the internal variability, and so this is there's a different type of information that they're presenting to the policymaking community as opposed to the scientific community. And which place are we standing in terms of our ability to communicate this particular type of information? Okay, so example 1, internal variability. We can further break down this information into internal variability. Here is the figure from Chapter 9. I guess I didn't include in my bio that I was an IPCC author this last time in Chapter 9, and so I have a particular affinity for looking at these figures, which might be sort of sadistic, but that's okay. All right, so example 1, global mean surface temperature. Now we see the wide range of all of the models which were used, all of their different colors, all of their different families that they were taken from. We also now see a direct comparison with observations out to the end of the simulations in 2012. And as a result, we can see that internal variability is defining the range that we saw in the previous figures. But we see that on interannual timescales, we have a lot of variability contributing to our uncertainty in any one given year, which is why the seasonal forecasting uncertainty is such a problematic issue in terms of the impacts community. So the response here is also a factor of natural forcings as well as anthropogenic forcings. And so on this slide, we have the identification of the major volcanoes that went off during the last 150 years and contributed to a significant cooling after each of these events. So we have Krakatoa back in the late 1800s, Santa Maria, Agung, El Chichon, and Pinatubo. And I know that El Chichon is in Mexico. Where is Agung? Indonesia, thank you. And most of these are major volcanoes in the tropics, which then are throwing up ash into the stratosphere and cooling the planet for about 2 to 3 years after the event happens, as the ash cloud settles out in the stratosphere as a result. The other example is the sea ice. And here we even see a much wider divergence in terms of the ability to match the multi-model mean that we have that's shown in red right here. There are several models that start off with very high sea ice extents and have very little response by the end of the 20th century. There are some models which start off with a low sea ice extent and are going down to almost 0 by the end of the century. Yes?
There's no bias correction in this figure?
There is no bias correction in this figure. Right, so this is the actual model response as distinct from its climatology. Whereas there is a bias correction in the previous one. And the bias correction is actually identified here on the right-hand side in terms of the global mean temperature for that particular time frame. So this is the 1961 to 1990 mean. And we can see that some models have 12 degrees base state climatology during that time frame. compared to a model here up above, well above 15 degrees. And that then leads to an uncertainty in its representation of feedbacks that are dependent upon the base state climatology as a result.
Sorry.
Yep.
Who's responsible for producing the M-LOST observational data set?
The M-LOST one?
Yeah.
M-LOST comes from the NCDC group in the US.
Okay.
They renamed it for some reason for this IPCC. Yay them. One more level of uncertainty. So the three different observational data sets are shown in black here. And the HAD-CRU-T data set has been in its 4th generation. The GISS temp data set from the NASA GISS group in the Goddard Institute for Space Studies group in New York City that was led by Jim Hansen for a long time and is now led by Gavin Schmidt. That's the solid long dashed line. And then M-LOST, it's a marine land observed surface temperature. I think that's what M-LOST stands for, but I don't actually remember that. So posterity, don't listen to me. Go check it for yourself. OK? Any other questions?
Yes, sir.
Yes.
The ash from the volcano, could it be surface temperature? Is it locally or globally?
So the ash from the volcano, when it goes off, the volcanoes that we're talking about here have to penetrate into the stratosphere in order to be significant on global time, on this multi-year time scale. And when the ash cloud penetrates past the tropopause in the atmosphere, it gets into the stratospheric circulation, and then it's transported globally. So you wind up with a global signal in terms of the ash cloud affecting everywhere on the planet, essentially. And then the ashes are then falling out on this 2 to 3 year time scale, given their basic fall velocity or terminal fall velocity of the size of the particles. But yes, it's a global phenomena, but it's a localized volcanic event.
So the baseline for this specific figure is 1960?
1961 to 1990. So that was the averaging time frame. And if you think about that, because that's this yellow band here is when the climatological period is, 61 to 90 is shown there. That means that if a model is over-predicting the response in the 20th century, it will diverge more at the beginning and more at the end of the time series because it's forced to be at the same climatology during that 1961 to 90 period. And that's a trick on your eye in terms of its ability to match the historical record. And so that's another optical illusion effect or a psychological effect that we don't actually anticipate when we communicate the science associated with or communicate these types of results. And that's one more added issue in terms of communicating uncertainties. You guys need more coffee, I can tell. All right. The last one is sort of going through the, whoops. The other component of uncertainty is the RCP scenarios. Is everybody familiar with them that I don't have to go through this? Or just raise your hand if you would like me to talk about it a little bit. OK, a couple people. Great. Well, I don't know if speakers are allowed to input, but so the RCP scenarios have replaced the SRES scenarios, which had replaced the IS-92 scenarios. So we've gone through multiple realizations from the economic community, making projections based on the population growth, the economic growth, the expected economic growth, the changes in the technologies, and then without actually dealing with the changes in the Earth systems, taking in those emissions and then creating a concentration or a net forcing associated with these particular scenarios. In this case, this time, they created something which is called a representative concentration pathway. That means all of the climate models now are using the exact same concentrations of the representative climate forcings. So CO2, methane, nitrous oxide, the chlorofluorocarbons, the additional, all of these gases which are essentially long-lived gases in the climate system are being provided to the climate models. And that means that the carbon cycle or the atmospheric chemistry component of the model is not necessarily being allowed to produce its own concentration as it moves forward in time. And that's part of the story here. They've identified these as radiative forcings at the year 2100. And so that tip 2.6 up to 8.5 is in watts per square meter. And if we wanted to compare them with the older results, I took this figure from it's the press release for the IPCC AR5 Working Group 1. I guess it's not actually on here. And so we see here now the big dots are the RCP scenarios. The dashed, the black triangles were the IS92A scenarios. That was sort of the central business as usual scenario as we go forward in time. And then we have on here also 3 of the SRES. SRES stands for Special Report on Emission Scenarios. It was also an IPCC process and designed to essentially sample a range of socioeconomic pathways moving forward over the next 100 years as to how the world might evolve, either as a very friendly community that would share technologies, and so everybody would be using solar arrays and wind power, or a very fractionated society in which only the most developed countries would keep their technologies and use them internally in order to improve their own economic development. So there's sort of a flat world economically versus a spiky world economically. And then, and then there was also issues related to the other socioeconomic issues that played out. High technology versus low technology in terms of them being developed. OK. And so that then led us to these, this new distinction of the RCP scenarios being used in everything moving forward. But if we want to trace the level of uncertainty starting in the early 1990s all the way up to the present time, we have 3 different scenario types that we have to concern ourselves with in terms of their overall response, or how the response of the system is changed when we went through these different for these different socioeconomic pathways. Have I completely confused you? Maybe. OK. All right. So far we've focused on internal variability and forcing uncertainty, and I'm going to leave a little bit of the introduction of the model response to some point in the future. I have 15 minutes left, correct?
We did start late.
Oh, you're going to give me extra time? That's not. We have to get a picture of us all, so I want everybody to be awake for the picture. Useful? Yeah. OK.
I'll let you decide
OK.
how useful you're going to be.
So I wanted to introduce these ideas of uncertainty if you haven't already come across these. I think Yoon already put these up on his slides, and so at some level I thought I didn't have to go over them. But there's a few things which I think are sort of philosophical issues. And so when you start seeing the literature on the language associated with uncertainty in the system, we run into a number of different things. And so I've put together this list. Everybody in the room probably has a different version of this list as to how they would address the levels of uncertainty. I think of observational uncertainty as going into the ability to calibrate our models and test whether the models are consistent with the record of observations. Observational uncertainty due to measurement errors and sampling distribution errors, temporal sampling issues are all leading to an uncertainty in the record of observations. We have our model uncertainty, the representation of the physics, the representation of the individual processes, the structural issues that our ability to understand the fundamental response of the system or processes in the system is characterized as epistemic uncertainty, or uncertainty in our basic knowledge of the system. And so that's coming from the philosophy community. Then we get into this issue of statistical uncertainty, which many of you in the room I think are better able to explain than me. I would call that random uncertainty, a stochastic process. but it's also referred to as aleatoric uncertainty, things which are unknowable. And those would be the things which are going to be surprises later on in your analysis. But we often think of them as, if we can characterize the uncertainty through a statistical process, that does not necessarily mean we have a combination of epistemic uncertainty, as we may not be sampling the true overall random effects, number of the types and sources of random effects. And that then, so we can separate out epistemic from aleatoric uncertainty. Do the statisticians like these terms? Yeah, fair to middling. OK. And then the last one is the one where the physics community, I think, gets involved. And our contribution to this started in 1963 when Ed Lorenz published his first paper on chaotic variability in the system, or sensitivity to initial conditions in a dynamical system. And so we call this chaotic uncertainty. We have a distribution of the way the Earth is going to be responding to this set of forcings over time. And we have this combination of internal variability or natural variability or unforced variability, which is contributing then to our ability to match the records of the observations to the model outputs that we have as a result. And so that's an important
So I
an important
sometimes group the statistical with the chaotic. Is there
I think they're fundamentally different pieces. And I think, especially when we talk about short time scale matching of the models for seasonal forecasting, for example, and so when we define our climatology as the 30-year mean at the end of the 21st century, then the seasonal variations in there might be, you could model that as a statistical distribution, of course. But if at any one moment in time you wanted to ask, are we getting the statistical distribution correct, we would have to say, are the models capable of actually making a prediction over the next several years in order to trust that the model is actually capable of doing the fluctuations at the end of the century. Yeah?
So I'm still confused about statistical uncertainty. Is that process noise?
Is that process noise?
Okay, so
I think it is, right?
Model uncertainty, I would understand. Maybe there is a fifth order process and you pick a second order process. That would be model uncertainty, right?
That would be structural uncertainty in my view, yep.
But the driving terms inside that model, which are statistical in nature, are those statistical uncertainty? Is that what we comply?
So I would say it's if you separate out the forced response of the system from the noise response of the system, how you characterize the noise at the end could be separated out into random noise, which is truly random in terms of getting down to the level of the observations and so on and so forth, and separate that from the internal variability component. That's how I would characterize it. But I think we're going to hear a lot more about this issue in the next week, I hope. Maybe I hope I'm giving food for thought for some of the other lectures. More questions? Other? Nope. OK. All right. I wanted to introduce the climate model structure a little bit here. One thing that we've been dealing with for a long time is this notion of a climate model hierarchy. In the 1960s, so this is sort of a climate model history lesson at some level. In the 1960s, we were dealing with energy balance climate models. We were also building the first general circulation models, which are being run on the supercomputers that we have today. But people like Budiko in Russia was building a climate model to look at the paleoclimate variations in the past. And people like Manabe and Weatherald and Jim Hansen and so on in the US were building the first climate models based on weather forecast models, which had were started to be developed in the early 50s and now being used to try and look at climatological situations. And so we have this range of complexity, and the simplest models being energy balance models. That's the fundamental constraint on the climate system in my view. Energy in from the sun is equal to energy out through infrared radiation. And if you're not going to get that right, we've done something very, very wrong with our model development. The next level we would talk about are these most complex models. And these are the atmosphere-ocean general circulation models, or Earth system models, depending on what your level of complexity is you've added into this, and I'll talk about that a little bit. This would be the state-of-the-art models running on the supercomputers, the major supercomputers of the world. And those would be the types of models we would refer to there. And all of the IPCC class climate models, Earth system models that we've talked about so far in the major figures of the IPCC are these types of Earth system models that we have here. We also have the models which are intermediate complexity models. And in 20 years ago, the carbon cycle was not a component of the major climate modeling communities. But you could build an intermediate complexity model which actually did include a carbon cycle and its uncertainties. And that was the community that I got into right after graduate school. And so the notion that you have a Earth system model doing as comprehensive a representation of the key processes and key feedbacks in the system, but not necessarily modeling it at the level of detail that you would have in a standard general circulation model as well. So GCM is often talked about as a global climate model, but its true history is as a general circulation model, which referred to the general circulation in the atmosphere or the average state of the jet stream and tropics in response to the tropical forcings. And so this notion that we have climate models being designed for very specific purposes, often these purposes are not including uncertainty quantification. And I think that's one of our goals here, is to taking the types of tools that are being discussed in this week's workshop and figuring out how do we apply these to the state-of-the-art climate models that we have available to us already. OK. If you haven't seen a description of a climate model, this is a nice figure that I've used. We discretize the equations for the numerical solutions of the governing equations for the planet. And so the grid boxes we see here are then, we're solving the fluid equations on this particular grid. We have within each individual grid box a set of physical processes which are unresolved. And those unresolved processes would include clouds, precipitation, the interaction with the land surface, the fluxes in and out of the ocean, so on and so forth. And those then would be the parameterizations that we often talk about in the climate models. And so we have the large-scale representation of the flow field given on the grid spacing that we see here. We have the individual processes, the parameterizations being solved internally to each of these individual columns or grid boxes that we see here on the sphere. I can go a long time into this, and I teach a class on climate modeling, and I guess the question is how far I want to go into details. If you haven't seen this, does anybody have any comments on things I should add to this process? Yes.
Very quickly, what is resolved and unresolved?
So the things which are resolved and unresolved? So the large-scale flow is resolved. The small-scale flow, which would be an example, would be a individual cloud convection system, would not be resolved. But as you'll see, the resolution of the models is improving, and therefore the processes which are being resolved is going to be changing over time. OK. So we have a model complexity is often at the highest level designated as atmosphere-ocean GCMs. Earth system models here, where we've now added atmospheric chemistry and the carbon cycle and vegetation changes. That would be considered an Earth system model. And if we add in the human societal dimension of the problem, this is called the IESM in the US community, but it's an integrating the economic factors into the climate model, into the state-of-the-art Earth system models, then would be something called an integrated assessment Earth system model. And the intermediate complexity community has been working in that realm for a long time. The full complexity models at the supercomputing centers are now starting to add in this level of complexity. and they found it's really, really hard. Okay. So here's a description of how we actually try and characterize, or what are our limits to understanding from basic computational costs in terms of limiting the understanding of uncertainty in the models. So there are three axes here. One, this is all referring to climate global general circulation models. On one axis, we have the resolution, what processes are actually being resolved. In this particular example, the oceans here are being modeled at 1/12 of a degree resolution. So that translates to about 10 kilometers in the ocean. And that's essentially the resolution that's required in order to actually model the Gulf Stream circulation in the ocean. So a key feature of the gyre circulation in the Atlantic or in the Pacific requires 1/12 of a degree resolution to actually model it at the way that we actually see it. Another issue is the level of complexity. What components are you actually including? The distinction between a model that includes atmospheric chemistry and does not include atmospheric chemistry would be an example of these different levels of complexity. And then the other question is what type of a analysis are you going to do? Are you going to focus on uncertainty quantification, in which you need to have repeatedly repeat the same experiment over and over again in order to get lots of ensemble members in order to look at the uncertainty in the response? Or are you interested in the very long time scale simulations, say out to 2100 or the year 3000, for example? Many climate models are now running out for 1,000 years and asking how is the ice sheet going to be responding to climate, but they're essentially only allowed to run one simulation for that 1,000-year period because of the computational cost involved with that. And so this here plane, this blue surface here is defining what we call the limits of your computational resources. And you have to then make a decision in your experimental design as to how best to use those resources. And that's what these three axes are attempting to describe as a result. Model complexity structure. I've already gone into this. The two major ones are if you're going to be reducing the governing equations, which are conservation of energy, mass, moisture, momentum, angular momentum, how do you actually put those equations into the model? And so that's its own issue. Resolution is also a structural issue. What's the finest grid scale that you're actually going to be representing? Okay, climate model history. These are the processes which were available to the IPCC class models during different time frames in the past. So the mid-1970s, carbon dioxide and rain processes were in the model. Many of the other processes were not. If we move on to the 80s, they added clouds. And they also added land surface, so a representation of the land surface. In the first assessment report in the early 90s, there was included instead of a representation of just sea surface temperatures being specified, there was an energy balance perspective of a slab ocean or a swamp ocean responding to the atmospheric fluxes above it. The second report added volcanic activity, sulfate aerosols that are reflecting particulates in the atmosphere, and then finally there was a dynamic ocean involved to get the circulation of the ocean included as a result. The third assessment report had a much better representation of the atmospheric chemistry components, the carbon cycle, the aerosols. Finally, rivers were actually feeding water into the oceans. There was a representation of the overturning circulation, that is the thermohaline circulation or the overturning circulation, depending on how you call it. And then finally, the AR4, we have atmospheric chemistry and interactive vegetation. Now, these are sort of the bleeding edge models in the AR4 and or cutting edge models, if you don't like that term. So these are the cutting edge models in and are now those sort of the basic models which were being used in the fifth assessment report. So there's not much more we can add except the actual human activity component that's driving all of these various features, I would say. The other issue is resolution. And here we have a representation of Europe and the North Atlantic and the tip of Greenland as it evolved through the various stages of the IPCC class models. So we have the first assessment report, 500-kilometer resolution for an individual grid box, all the way up to the fourth assessment report here, where we had models which were running at approximately 110 or 1 degree resolution. And you have both the grid box scale given in kilometers or the spectral resolution given as a T21 or a T106 spectral representation of the fluid equations in the model itself. And I would say that these were the best resolutions at that particular time. And if we go on to the next fifth assessment report, now we're seeing that the representation of Europe at 87 or 87.5 kilometers is shown on the top. There are models running at regional scale resolutions, which are at 30 kilometers. And who's running a model at 5-kilometer resolution? 10? 20? OK, so we're seeing that the highest resolution models are getting down to this very fine scale resolution, which then means that the forcing of the atmosphere by this lower boundary condition is going to be much more representative of the real system. So I'm going to take a few extra minutes. My apologies, but the last thing here is if we asked what are the major contributors to our uncertainty. I already mentioned this at the beginning, but we have the implementation of the numerics in the system. How are we solving the numerical equations, the partial differential equations that we have? And are the uncertainties in the solutions to those equations small or large? Depending on who you talk to, we would say they're smaller than, these are sort of relative quantities, I think, within the climate community. If you talk to an applied mathematician, they might say that the errors are large. But of course, you have to specify what's large mean. And so I think that's part of the story here. So implementation of the numerics tends to have a small overall contribution to the uncertainty. Representation of the dynamics that's resolved is a small contribution overall. But the dynamics that's embedded in the subgrid scale processes is where you have some of the largest uncertainties. And that has to do with things like the cloud distributions and so on and so forth. Natural climate variability, that's this initial condition uncertainty that we were talking about. Both of these are, I would say, the major contributors to our uncertainty in the response of the climate system overall. And then the issue of the atmospheric composition, that is the aerosols and the small particulate matters, which have very short lifetimes, in addition to the uncertainty in the greenhouse gases themselves. Methane has a lifetime of about 10 years. CO2 has a lifetime of about 100 years in the atmosphere. And there are some gases which actually have 10,000-year lifetimes. You put them in the atmosphere and they stay there forever virtually. And so, so that's another contributor overall. OK, I'm going to skip this. We've already talked about this at some level. There is going to be a lot of discussion about these things in other lectures overall. There's the language of the intercomparison projects. Model intercomparison projects have been used to assess structural model uncertainty for a long time. And so I would identify here that we have they're specifying specific scenarios that each modeling group will contribute to this intercomparison project as it's being designed. And that process is now ongoing for the next IPCC report. The models that are used are the best models from individual groups. And that means that you're not sampling the uncertainty of the models themselves. You're sampling the uncertainty in terms of what does each individual modeling group think is their best model. And that's not necessarily the same issue. So this is sampling the structural uncertainty as a overall. here is a list of MIPS. Some people have MIP overdosing. So you can get overstimulated by the number of MIPS that are out there. And the last thing I wanted to get to is this, what does characterizing uncertainty mean? And I wanted to leave you with this idea in terms of summarizing all of these sources of uncertainty using a very simple model, which I call the dice model. I have two dice, and that's my climate model right down here. And I don't know why that's on the top up there, but there it is. So this is my representation of the world. We roll the dice to predict some future event. And if we want to start understanding these sources of uncertainty, we get into the issue of the predictions have multiple sources of uncertainty. And so this gets into the aleatoric uncertainty. We get a new random number the next time we actually roll the dice. We also include the epistemic uncertainty. The basic knowledge of the system is unknown, whether or not we're talking about Europe. For example, we roll the dice in Europe, or we roll the dice over South America in the previous slide. We're going to have a different representation of those particular physical processes, and we may be uncertain about those very specific ones. Or we have lots of uncertainty associated with getting the model right due to the initial conditions. So we now roll the model. Here I have 30 dice. I roll the model 30 times, and we now have multiple conditions, multiple initial conditions contributing to the overall uncertainty in our estimate of the climate for the world. The last one is the epistemic uncertainty of getting the model right, not just for the right reason, but for the right structure. Every one of these die on here, these dice is every die on here is, there we go, a six-sided die. And therefore, it's basically trying to predict the same distribution. But if you'll note, there are corners, there are edges, there are curves. Not every die on here is the same. It may or may not have the same distribution given the structure of the six-sided die that's being rolled. So we have to get the model physics right. However, we may not even have the model structure right. So instead of a six-sided die, we can go to a multi-sided die. So on here we have a four-sided die, which is the tetrahedron. We have an eight-sided die here. We have a 30-sided die down here on the bottom. And then we have this big thing in the middle, which I call an infinitely sided die. And so these are the structures that we can actually create. Now the problem is, what if the world is actually this?
Sorry, what do you mean by the structures?
The structures?
The model structure, right?
So in this case, the model structure is, are we rolling a die here which provides 8 possible values, or 6 possible values, or 50 possible values?
And what's the analog?
And the analog in the real world is that we go to higher resolution. We get more. We go to more possibilities as the way say Europe can respond to climate change in the future. If we resolve more and more processes, we now have more and more physics which can contribute to the overall uncertainty in the system.
But what's the sweet spot?
What is the sweet spot? It depends on the problem you're trying to predict. I can't go any further into it than that until you have this exchange with the impacts community who says, I need to predict precipitation for my river to understand the possible flood forecasting in this location. Or we were wandering around Venice for a day or so, and there are well-known floods that hit Venice 90 days a year, and that's expected to increase to an even larger number in the next 100 years. And we need to know what processes are required in order to actually predict the floods of Venice. Is that helpful? OK. Thank you for stopping me. I go by this too fast, and everybody wants coffee. So it's a good question. OK. So this is the other question is that we may not know the right structure. It may not be a dice at all. because that's what the real world actually presents. These are the clay dice that my son produced in a pottery class. They actually have the right numbers on them, but it's the structural issue. So this is multiple levels of uncertainty, aleatoric as well as epistemic uncertainty. And then the last issue is, I haven't brought in, what if we're actually observing it this way? We have a very fuzzy view as to what the actual world looks like if we're not observing all of the various components of the system. I think the saving grace here is, at least for the physical systems, we think we understand what the physical systems and how they behave are. Whereas if we talk about human systems, I think the story is that an electron doesn't wake up tomorrow and think that it should behave differently. Whereas a human can wake up tomorrow and say, you know, I might like this. Maybe I'll go do something else today. So those are the basic stories. So thank you for listening. A few extra minutes. Any questions or at this point? Yes.
You were talking about the concept of model hierarchy before.
Right.
And you were saying that there are the IUGCMs and then there are the system models which include carbon cycle feedback, things like that. But you're saying in the 7.5 ensemble that includes models when you look at the AR5 plots, which are full system models and also ones which are just
Yes.
IUGCMs. Do you think it's appropriate that they're grouped together
No.
for a full multi-model ensemble spread?
Personally, no.
Okay.
I don't think they're appropriate. I think you have to be very specific about what uncertainty you're trying to represent by those ranges that are presented in those results. So the IPCC in later chapters actually tries to go through this, embedded in the material, what the effect of the carbon cycle inclusion is and on the results. And so in the summary for policymakers, it's all lumped together. And I think if you took with and without the Earth system models, it probably wouldn't be all that different. But I can't claim that that's true. Good question. Yes.
I wanted to come back to this division of the classification of the errors. And one example, when I pick up on this, your slides with the different assessment reports, complexity, and you pointed out the one-stage volcanoes were included. As I understand, the volcanoes were included in the simulation of the past climate up to the present, but of course they're not included in the future runs out to 2100 because you don't know when they're going to occur.
Right.
So I was just wondering, using that as a set example, where you would classify that, because in some respects it's a lack of a process in the model.
Yep.
On the other hand, it's something that you can't determine when it's going to happen. So even if you had a perfect volcano parameterization, it would still be a stochastic process. So would that, in your classification, would that actually then classify it as one of those, a non-Gaussian random error in that third category? Because even if you include it, it has to be included in a stochastic sense in the models, which is not done at all.
Right. So in the weather forecasting community, I think that the terms are that you can't assess a probabilistic forecast with a single run. You have to assess it probabilistically.
Right.
And I think the same is true for climate as you move out into the multi-decade or century-long timescales. And there are volcano generators, let's call it that, which actually do produce a time series for the future, which is internally consistent, let's say, with the ice core records in terms of their strength of volcanoes and the locations of the volcanoes depending on where they went off. So I think those are we have to start recognizing that that's going to happen in the future. The other side of this is that the community has always said these are the anthropogenic changes, and they've chosen to ignore the volcano in the future by saying this is the uncertainty associated with the anthropogenic factors given the response of the system, and that then the uncertainty of having a volcano go off, if they go off in rapid succession, they're going to be cooling the ocean dramatically and putting the Earth into a different trajectory. Whereas if they go off every 10, 20 years, the system kind of comes back to its old equilibrium. And so this particular issue is going to play a role in the future if we got very unlucky and had a lot of volcanoes going off all at once in a clustered sense.
But would you classify a model that emits that? Would you classify that as a random error, or still would you classify that as a structural error in the model?
I think if they're not including it, it would be a structural error in the future. If they are including it, then it would be a random error, or a random component which is added on as an additional forcing of the system, which then you would then have the response. Yeah, I haven't thought about that too well. Yep. One more question, and then we'll finish.
That the RCT was one way to constrain the uncertainty compared to the old scenarios.
Mm-hmm.
We know that model resolutions are crucial when it comes to the outcome of the global circulation. Would it be a sensible thing to do to constrain the model by saying at 10 GCMs running the same resolution?
Would it be reasonable to
constrain the resolutions of the ones like we have this 30 plus GCMs for the AR5? Would it have been better if we said that all these GCMs to be run at the same resolution, given the same masterpiece, we could have come with a spread? Knowing that all resolutions is crucial?
I mean, I think there are subset experiments that the model under comparison projects are doing like that to test the issues of resolution, and I think those are being done as an end goal of producing a range of uncertainty for the end of 2100 or 2300 or 3000, putting the best models of it that you have available to the task has been the standard approach, and that thinking about it as resolution dependence is more of a scientific goal, not necessarily relevant to the policymaking process, which the IPCC has taken on as its purpose. Okay, thank you so much.